Hi, welcome to my channel. In this video, we want to solve the following problem. ABCD is a quadrilateral inscribed in a circle with a radius of 3 units. The line segments AC and BD intersect at E such that EC equals 2AE. Given that AB equals square root 3 times AE, BD equals 5 units, find the area of ABCD. And now for the solution. First, denote the area of ABCD as this. Then, area of ABCD equals area of ABD, which is this blue region, plus area of DBC, which is this red region, where area of ABD equals area of AED, which is this triangle, plus area of ABE, which is this triangle, and area of DBC equals area of DEC, which is this triangle, plus area of EBC, which is this triangle. Next, focus on triangles AED and DEC. They share the same height, which we will denote as h. Area of AED is then given by half times h times AE, while the area of DEC is half times h times EC. Since EC equals to AE, area of DEC equals half times h times 2AE, or 2 times half times h times AE. Therefore, area of DEC equals 2 times area of AED. Similarly, for triangles ABE and EBC, they share the same height, and since EC equals 2AE, area of EBC equals 2 times area of ABE. Thus, area of DBC equals 2 times area of AED plus 2 times area of ABE. And since area of ABD equals area of AED plus area of ABE, area of DBC equals 2 times area of ABD. This implies that area of ABCD equals area of ABD plus 2 times area of ABD. And so area of ABCD equals 3 times area of ABD. Therefore, calculating area of ABCD amounts to calculating area of ABD. Let's take another look at triangle ABD. We are given that BD equals 5 units, which is the base of the triangle. Therefore, to calculate the area of the triangle, all we need is the height of the triangle, and we are done. Let's start by considering the line segment AEC. We are given that EC equals 2AE. Since AC equals AE plus EC, thus AC equals AE plus 2AE, or 3AE. Next, consider the equation AB equals square root 3 times AE. Squaring both sides, we obtain AB squared equals 3 times AE squared. Next, we write the left hand side as 3AE times AE. Since AC equals 3AE, we have AB squared equals AC times AE. Following this, we divide both sides by AB times AC to obtain AB over AC equals AE over AB. Next, consider this part of the diagram, which consists of triangle ABE and triangle ACB. Let's show that triangle ABE is similar to triangle ACB. The left-hand side of this equation is the ratio of the side AB of triangle ABE to the side AC of triangle ACB, while the right hand side is the ratio of the side AE of triangle ABE to the side AB of triangle ACB. Furthermore, this angle is common to both triangles. That is, angle EAB, which is the included angle of sides AB, AE of triangle ABE, equals angle BAC, which is the included angle of sides AC, AB of triangle ACB. Therefore, by the side angle side or SAS similarity criterion, the two triangles are similar. Since angle ABE, which is this angle, and angle ACB, which is this angle, are corresponding angles in similar triangles, we have angle ABE equals angle ACB. Next, focus on this part of the diagram that consists of the line segments AD, AC, BD, and BC. Angle ADB and angle ACB are angles subtending the same arc. Since angles subtending the same arc are equal, we have angle ADB equals angle ACB. Finally, focus on triangle ABD. Since these angles are equal, the triangle is an isosceles triangle. Denoting H as the midpoint of BD, the line segment AH is then the height of the triangle. Thus, we want to calculate AH. To do this, observe that AH is also the perpendicular bisector of the chord BD. Recall that the perpendicular bisector of a chord passes through the center of the circle. Thus, denoting the center of the circle as O, let's extend AH to O. Then connect O to B. Since the radius is 3 units, the length of OB is also 3 units. Since the length of BD is 5 units, the length of BH is 5 over 2 units. Using Pythagoras theorem, we have OH squared plus 5 over 2 whole square equals 3 square, or OH squared plus 25 over 4 equals 9. Subtracting 25 over 4 from both sides of the equation, and then taking the square root, we obtain OH equals square root 11 over 2. Since OH plus HA equals OA, and OA is the radius of the circle, we have square root 11 over 2 plus HA equals 3, or HA equals 3 minus square root 11 over 2. The area of ABD, which is half times BD times HA, thus equals half times 5 times 3 minus square root 11 over 2, or 15 over 2 minus 5 times square root 11 over 4. The area of ABCD, which is 3 times the area of ABD, thus equals 3 times 15 over 2 minus 5 times square root 11 over 4. Therefore, the area of ABCD is 45 over 2 minus 15 times square root 11 over 4, which is the solution to our problem. As an exercise, try to solve this problem and see if you can get the correct answer. This marks the end of the video. If you enjoyed this video, please leave a like and subscribe to my channel for more content. Thanks for watching and see you all next time.